Welcome to my walkthrough of the 2019 Unified Chemistry exam on the OCR specification. If you do use this video to revise, I would really appreciate it if you could leave it a like before you go and consider subscribing to stay updated. Check out the information in the video description for more revision tips. Starting off here with question 1, which has a similar structure to a lot of these question 1s on the Unified Chemistry exam. It's a question made up of lots of sections that are seemingly unrelated to each other, and they all challenge a different part of the A-level. For example, part A looks at molecular geometry and electronegativity, part B looks at isotopes, and part C here looks at partial pressures, which we encounter in the equilibrium topic. So here we've got a lot of difference all the way through in terms of content, and I suppose this is kind of this exam's version of multi-choice questions, but that's not going to mean that it's always going to start out this way, but it has done on a couple of occasions. See the 2018 paper for a good comparison. First off, we're being asked to explain why a molecule of CF4 has got polar bonds, and that's because fluorine is more electronegative than the carbon, but doesn't have an overall dipole, and that's because the molecule, since it's tetrahedral, is symmetrical, and therefore the dipoles cancel. The bit in brackets wasn't required by the mark scheme, but I have seen it on other papers, so I've put this in there to give you a full answer. Explain why a small proportion of molecules in water have a relative molecular mass of 20. We've not changed the formula, it's still H2O, so how do we get 2 more atomic mass units on there? Well, it's because of isotopes. And specifically, I would have thought that you would go straight to the idea of deuterium, especially if you finished Module 6 on the specification, since we learned a little bit there about D2O and NMR spectroscopy. However, they did allow any discussion here of oxygen or hydrogen isotopes to explain the answer. Next up, what is the partial pressure of oxygen in pascals in a gas mixture containing 21% oxygen by volume and with a total pressure of 1 × 10 to the power of 5 pascals? This is a bit of a weird question, but it's a nice application of what does mole fraction really mean, comparing it to this percentage by volume figure. Well, 21% of 100% is a little bit like a mole fraction in a way. All your mole fractions in a sample of gas should add up to 1. And so if you consider that all the percentages of gases should add to 100%, we can tweak that 21% to make it a mole fraction. So the mole fraction here of 0.21 has been achieved by this 21% figure. To get the partial pressure of a gas, we take its mole fraction for the equilibrium mixture and we multiply it by the total pressure. Don't tweak the units if you don't have to. Correct answer here is 21,000. Next up, what mass of carbon dioxide in grams is formed by the complete combustion of 42 meters cubed? A bit unusual to see meters cubed, if I'm honest. Measured at room temperature and pressure. That's a massive clue right there. And as you can see, I've labelled that. Massive clue. Of propane, C3H8. They've not given you the formula for propane. It's not a very difficult alkane to know the formula of, but still it's a bit high demand in terms of access here. They've not told you what kind of calculation to consider or to use. They've given you lots of information with regards to the units just here. They've also given you meters cubed up there. They've given you RTP here. It's quite a lot to access the question really, isn't there? So I'm going to kick off here by figuring out how many moles of propane I've got, and this room temperature and pressure information is really helpful here because it means I can use the molar gas volume. And so if I do the volume in centimeters cubed, so I need to convert this meters cubed value to centimeters cubed by timesing it by 1,000,000, and you can see I've got that on my numerator just there. I then divide by 24,000 because I know that's the molar gas volume in centimeters cubed, and it gives me a value of 1,750 mole. Now, to convert that into a mass of carbon dioxide, what I now need to do is multiply by 3, since the combustion of the propane is going to have a 1:3 ratio between itself, the fuel, the C3H8, and the carbon dioxide. And then I multiply by the molar mass of carbon dioxide, which is 44, and that gives me a mass value of 231,000 grams. My answer will come out in grams because I've used grams per mole here for my molar mass, and I've got just a regular mole value. Part E A reaction is first order, so remember that means that the change in rate is directly proportional to the change in concentration with respect to the H plus ion. At a pH of 1, the initial rate is 2.4 times 10 to the power of negative 3 moles per decimeter cubed per second. What's the initial rate at pH of 3? Right. So what we need to first consider is what I've written in the red just here. Going from a pH of 1 to 3 is a divide by 100 on the concentration of the hydrogen ion. You can actually run this through yourself if you have a quick look at these. 0.1 mole per decimeter cubed H plus has a pH of 1, and 0.001 mole per decimeter cubed H plus has a pH of 3. So that divide by 100, if the concentration of H plus has divided by 100, then the rate will have divided by 100 as well. And that takes me to my answer of 2.4 times 10 to the power of negative 5. And remember, that directly proportional change is because we're told it's first order. Moving on here to part F, what is the number of oxygen atoms in 4.26 grams of P2O5? I think this is remarkably simple considering that it's actually 2 marks and compared to the previous page of questions, but here we are, let's just roll with it. First off, we need to figure out the number of moles that we have of P2O5, and that's done by doing mass divided by molar mass, as you can see just there. So that gives us a value of 0.0300 mole. Then what I need to do is consider that that number of moles represents the P2O5, but I'm interested in the oxygens. So how many moles of oxygen atoms do I have? Well, I just multiply the value of moles that I've just calculated here by 5. And that gives me a value of 0.15 mole of the oxygen atoms. To convert that then into a number of atoms, so I've got my moles of atoms at the moment, but then to convert it to a number of atoms, I multiply by the Avogadro constant, which can be found on your chemistry data sheet. The correct answer here is 9.03 times 10 to the power of 22. And since I was given no precision requirement, what I need to do is match the minimum precision that's been used by the question, which in this case was 3 sig fig. We then move on to question 2, which is really quite a challenging question. There's a lot to be said for this question in terms of its complexity, and it does require lots of careful reading. Especially at this point, especially in the Unified Chemistry exam, read a question once and then read it again. Don't obsess too much with highlighting parts of the questions and making annotations. Concentrate on reading for information and then approach the question. It's very easy to rush ahead and miss a crucial piece of information. Like in this one, we've got things like density, we've got references to certain conditions. Let's pay close attention. Benzoic acid is added to some foods as a preservative. A student prepares benzoic acid outlined below. We've got the student mixes 4 centimeters cubed of phenyl methanol. We've got the formula there. That's actually a primary alcohol group, which is going to be important later. And we've been told the density here is 1.04 grams per centimeter cubed. And they're going to react that with some sodium carbonate and aqueous potassium manganate 7 as an oxidizing agent. So that's a different oxidizing agent than the one we are typically shown on the OCR spec, which is acidified potassium dichromate 6. And the mixture is heated under reflux. Please note that this is an alkali condition set, which is quite different. The resulting mixture is cooled and then acidified with concentrated HCl. Now it says acidified, it doesn't say that there's some sort of substitution or anything else taking place here. We're just acidifying it. So this could often just mean that we are protonating the sample. Maybe it was deprotonated because of the alkali conditions, for instance. The student recrystallizes the impure crystals to obtain 1.59 grams of pure benzoic acid. Excellent. Okay, part A. In step 1, sodium carbonate makes the reaction mixture alkaline. It sure does, already mentioned that. Write an ionic equation to show how carbonate ions form an alkaline solution in water. Okay, an alkaline solution is one which contains OH minus ions. So, if we're writing out this, we know that we've got our initial reactant of the carbonate just here. We're going to suggest that we've got water, because we're being asked to show how the mixture is alkaline and it's how carbonate ions form an alkaline solution in water. So I'm going to assume water is my other reactant there. I have to make the hydroxide ion. That's absolutely crucial here because that's the whole point of the question. And then the HCO3 minus is everything else that I haven't used, but with that singly negative charge, because remember the left-hand side is 2 minus and each side needs to have the same overall charge. So it's not a reaction equation that's actually distinctively on your A level, but it is described quite well by the question. And it's very similar to the equation that we see for when ammonia gets placed in water. So if I just jot that out here, I will delete it straight after this, but we've got ammonia, NH3, reacting with water in an equilibrium to produce NH4 plus, the ammonium ion, and OH minus. And that's how the ammonia is considered an alkaline solution with water, because it's got that OH minus ion on the right-hand side. So there is a little bit of crossover there, I suppose, as well. And let's get rid of that. In step 2, explain why the mixture must be acidified so that the crystals of benzoic acid appear. And it's because adding that acid, as I mentioned before, is reacting with the carboxylate group. So if I just circle that up just here, the benzoate group just there, and it's protonating it. Write the overall equation for the preparation of benzoic acid from phenyl methanol. Use O in square brackets for the oxidizing agent. This isn't wildly different at all from anything you've done. It's just interpreting the formula. I would personally give skeletal. I love a bit of skeletal, and we've not been told to use a specific style of formula, so that is fair game to consider. You could do exactly what they've done here, though, in the blue, which is more in keeping with the type of formula you've already been given by the question. Could be easier for you, I'm not sure. Just make sure with this that you have considered that this is a primary alcohol group, please, as I mentioned before. So there's the new carboxylic acid. I need 2 moles of this to make it balance, and don't forget your H2O. Next up, quite a big calculation here with, honestly, I know it's an exam. I know it must have been horrific for the students who sat this because it is quite confusing, but this is absolutely excellent. I can't wait to get to that. Calculate the percentage yield of benzoic acid. Give your answer to 3 significant figures. So, in order to do the percentage yield, we need the actual divided by the theoretical times 100. And I like to use moles for this. So the actual moles of product achieved divided by the theoretical moles of product that could have been formed times 100. And that's actually shown, there we go, down here at the bottom. So my actual mass achieved, described by the question, was 1.59 grams. So that is mentioned up here. If I just go back up there, there we are. There it is, 1.59 grams. So I'm going to convert that into moles, and it's of benzoic acid. So over here, as you can see, I've got 1.59 divided by 122. That's the molar mass of benzoic acid on the denominator there. And it gives me a number of moles have been actually achieved. So this is going to be my numerator in the grander calculation down here at the bottom of 0.0130 mol. Then I set to work on the theoretical moles. So we've got to start off with our reactant. I'm actually going to use this equation that I have constructed just here. So for every one of these that reacts, one of these gets made. So for every one of the phenyl methanol that reacts, I get a benzoic acid. So I start off by finding how many moles of the phenyl methanol I'm actually using, and that's found by doing mass divided by molar mass. But they've been really sneaky with this. I just think it's really sly, but it's actually quite clever. In step 1, you're told that there's 4 centimeters cubed of phenyl methanol. Now, the temptation to find moles when you see a volume like that is to do moles equals concentration times volume, but they've not given you enough information. So what actually you need to do is use this density quantity over here to get to a mass. The density calculation is not really part of your A level, but it comes up a lot in exams, and you're expected to be able to interpret units as a way of getting a quantity. So it's not completely unfair to include it. It's just a bit of an extra challenge. Here, for example, in order to get the mass of the phenyl methanol, what I'm having to do is the centimeter cubed value for that solution, for that substance, multiplied by the density. So I'm doing 4 centimeters cubed multiplied by 1.04 grams per centimeter cubed, and it gives me my numerator here, which is going to be my mass of the phenyl methanol. I then divide that by 108, which is the molar mass of the phenyl methanol, and it gives me a number of moles of 0.0385 mol. That's equal then to the number of moles of benzoic acid, as they're in a 1-to-1 ratio with each other. And that's my theoretical mole value that I could have achieved. I then do my fairly standard percentage yield calculation of actual moles divided by theoretical moles times 100, and it gives me 33.8%. There's quite a few stages to this, so the mark scheme did also allow 33.9%. This is, I think, quite unfair because they've asked this same thing before in a level of response question and given significantly more credit for it. In step 3, describe how the student can recrystallize the impure crystals to obtain pure benzoic acid. Here, you wouldn't really list this as 2 bullet points, but I want to show you how it was split up in the mark scheme. Dissolve the solid in the minimum amount of hot solvent is crucial, and then cool the sample, filter it under reduced pressure is the best way to do this, and that's using a Buchner funnel and a Buchner flask, for instance, and then leave it to dry. So this could be dried in an oven, or it could be dried, it could be air dried over time. You can leave it in a fume hood, for example. Moving on to question 3, this question is about elements and compounds in group 4 of the periodic table. There are 4 oxides of lead, PbO, PbO2, Pb2O3, and Pb3O4. A student carries out an experiment to identify an unknown lead oxide, which is one of the 4 oxides of lead shown above. The student plans to reduce the unknown lead oxide to lead, and I've highlighted that because it's important later in the question, by heating the lead oxide in a stream of methane gas. So the lead oxide and the methane are going to be reacting together, and you're definitely going to get lead as one of the products. That's a lot to take in there, so I'll just reiterate some of those points for you. We've got that the lead oxide, we don't know which one it is, reacting with methane in this tube, and we're going to see lead as one of the products. We've not been told or asked to consider what the other products would be just yet. Student's method: weigh an empty dish, add the lead oxide to the dish and reweigh it. Set up the apparatus and pass methane gas through the tube, heat it for 10 minutes. Pass cold air through the tube to cool the dish and its contents, weigh the dish and its contents, and then the questions kick in. Write the equation for the reduction of Pb2O3 with CH4. So we know they're reacting together. Now we know we have to produce Pb. We know we have to produce lead. We're told that by the question. And the remaining atoms we have are carbons, oxygens, and hydrogens. The instinct you should have here is, rather than making one big stack of nothing, you should try and make CO2 and H2O. Balancing it then takes a bit of time. I do think the effort for this question is worth more than 1 mark. It's potentially worth coming back to it later because it doesn't really impact the rest of the question, but it is high challenge because it's unified, and especially with that setup since you don't know the products. All the more reason not to spend as much time on it though. You could be balancing it for ages. Please bear in mind you're not 100% sure perhaps that your products are correct. The student uses safety glasses and a lab coat. State with a reason one other important safety precaution the student should take when carrying out this experiment. Look, lead is toxic, and whenever something's toxic in a lab, you should be wearing gloves. The other thing that they did accept, which makes sense as well, is methane is flammable, so you should keep it away from the flame. Next up, the student was not sure that all the oxygen had been removed from the lead oxide. Suggest 2 modifications that the student could make to their method to be confident that all the oxygen had been removed. Explain your reasoning. This is associated to some of the moles work you do at the start of your course in Module 2, and your go-to phrasing should be to heat to constant mass to begin with. Then I'm going to suggest using excess methane. So if you've got excess of one of the reagents like methane, which is being passed through the tube, I would really go as that as my go-to alternative. There were lots of other things here, such as using powdered lead oxide instead of a lump, for example. Check the mark scheme for more alternatives, although these 3 were the ones I would expect you to go with. Moving on to part 4 here, and we've got loads of data to pick through. The student makes suitable modifications to the method and repeats the experiment to obtain the accurate results shown below. We've got mass of a dish and the lead oxide, and then dish and lead at the end of the experiment. And as you can see here from my annotations, we can get lots of different quantities here. The top 2 numbers can be used to get the mass of the lead oxide. The bottom 2 numbers can be used to get the mass of oxygen, which you might not have considered. And the purple one, so the top and the bottom one just here, can actually be used to get the mass of the lead. So we've got loads of information here from the data table, which only contained 3 values in to begin with. Calculate the empirical formula of the lead oxide. So this is quite a typical empirical formula calculation. We've got lead and oxygen because those are the 2 elements that are inside our formula here, and empirical formula calculations typically just use the elements. And so I've got mole calculation for each of them using data in the table. So you can draw where I've got the data from there. And then divide by the smaller number of moles out of the 2 to get me a ratio, and that ratio is 3 to 4. The empirical formula, therefore, for my lead oxide here is Pb3O4. Next up, silicon dioxide and carbon dioxide are oxides of other group 14, group 4 elements. Solid SiO2 melts at 2156 degrees C, and solid CO2 melts at -56. Suggest the type of lattice structures in the solid SiO2 and in the solid CO2, and explain the difference in the melting points in terms of the type of force within each lattice structure. Occasionally here what they've done is they've said types of force and particle, and in those scenarios you would also talk about distinctively. For example, if you were saying covalent bonds were the type of force, you would talk about how those covalent bonds are between atoms. And if you were talking about things like London forces as being the force, you would talk about how they are between molecules. So watch out for that, where they say types of force and particle. The structure in SiO2 is a giant covalent lattice structure, and the structure in CO2 is a simple molecular lattice structure. We're not suggesting giant ionic lattice for the SiO2 because silicon isn't a metal. We're going to go for that giant covalent lattice structure, which is what silicon has as well. For the CO2, that melting point is so incredibly low. That just tells me that I'm only breaking weak intermolecular forces there. In terms of my bullet points for the explanation, the forces being broken in CO2 are London forces, which are an intermolecular force, and in SiO2, the forces are covalent bonds. The London forces are weaker than the covalent bonds, is my clear comparison between the 2. Moving on to question 4, and this one's about Dettol. Dettol contains an antiseptic molecule called chloroxylenol, got that right, which is shown just here. Now, throughout this question, because you have to refer back to the structure quite a lot, I'll draw extra little snippets here, and I'll always put these in a red box. If you see it in a red box while I'm going through this, it wasn't actually in the question at that point. I've just pasted it in there so that I can use it to explain my answer. All right, so just watch out for those red boxes. So it's a disinfectant containing this molecule just here. First off, what's the systematic name? That's often the IUPAC name. It's another way of saying the same thing, essentially, of the chloroxylenol. Now, the phenol group is considered highest priority here. So it's an oxygen-containing group if you're looking for a rule of thumb at A-level. And so we don't need, especially for phenol, to put any locant number in the name. So I'm just going to avoid that. And then we number round the ring here to get the smallest combination of locant numbers possible. Since the molecule is symmetrical, we don't need to worry too much about that. Just make sure that when we look at the name, we've got 4-chloro to describe the fact that the chloro is at position 4 on the ring. 3,5-dimethyl to describe these 2 methyl groups just here at positions 3 and 5 on the ring. And then the phenol bit, it's implied for phenol that it would have been the first carbon in the ring. Predict the number of peaks in a carbon-13 NMR spectrum of chloroxylenol. So I've done the molecule again just up here. And what I've done is I've gone through the molecule, first off looking for a line of symmetry. And you can see here with this dotted line right the way through, you can see we do have a line of symmetry. And I did mention that before actually as well. What we're now looking for are non-equivalent carbon environments. I've got one just here at the top. Now these 2 carbons, circled them up together here, as you can see, are equivalent environments, so they would give one peak. So that's my second peak. And the same is true for these two that I've circled up here for number 3. So I've got 3 peaks so far. One for this fourth one at the bottom just there. And then these two CH3s are identical or equivalent environments, I should say, and they give the fifth and final peak. So the correct answer there is 5. Next up, name the functional group responsible for the acidity of chloroxylenol and describe a simple chemical test which would confirm the presence of this group. I think this is a weird question, really weird, because there is actually a chemical test that you can use which isn't on your A-level for this, and it is mentioned in the mark scheme, but I'm going to stick to the mark scheme one because you would have to use your specification knowledge to answer this question, so I want to show you where that does link to your spec. Now, looking at the molecule, it is this OH group at the top just here. That's actually acidic, so it looks like an alcohol group. It's a phenol group, and so you might not recognize that as something being acidic, but you are expected to know that phenol is acidic, and it would have that pH, therefore, of less than 7. However, it's not quite acidic enough to react with a carbonate, and that's the chemical test. I'm using a pH meter here specifically to remind you that pH meters exist, but also because that's our best way to get that pH level indicated. Moving on then to part 4 of our question, and we've got a student measures the pH of the contents in a bottle of Dettol as 5.14. We've got some extra information now here as well, that the label on the bottle shows the percentage of chloroxylenol in Dettol as 4.80%. That's a bit confusing, really. We don't get that very often in a chemistry exam, but thankfully they've given us this little supporting statement just here, explaining that what that means is for every 100 centimeter cubed of Dettol, we've got 4.8 grams of the chloroxylenol, and I've replicated the structure here of that because I'm going to use that to answer the question. We've then been told to assume all the following information in the bullet points. That chloroxylenol is the only acidic component in the Dettol, which is important because that means we're only considering it as the acid towards that 5.14 pH at the top. We've got that chloroxylenol is a weak monobasic acid. Good, that means we can assume that partial dissociation. And it's monobasic, which means only 1 H plus per molecule of acid is donated. And the density of Dettol is 1 gram per centimeter cubed. We don't need to do anything with that. It's almost just assuming that 1 gram equals 1 centimeter cubed here, and it just means we don't have to worry about density. We've been instructed then to write the equation using molecular formula, very specific, for the acid dissociation of chloroxylenol, and then separately calculate the acid dissociation constant, the Ka, for the chloroxylenol. First off then, using my formula from earlier in the question, I've got my molecular formula equation just here showing the dissociation of the chloroxylenol. It's a weak monobasic acid, so equilibrium, single proton, conjugate base, which is just the deprotonated chloroxylenol from the left. Then my calculation. A Ka expression for a weak acid in solution, if we just have a quick peek at it here, has got an approximation that we can make. So this isn't a buffer, this is just of a weak acid. And you'll notice here I've got a numerator which has got a squared feature to it. Now that value here, I'll explain shortly how I get to it, is the H plus ion concentration. And I'm squaring it there because we're assuming that the H plus ion concentration is roughly equal to the A minus ion concentration, or is equal to it. And therefore I'm able to square the numerator here, and I don't need to worry about trying to find a value for the A minus ion concentration for that conjugate base concentration in the solution. Then the denominator is actually the concentration of the weak acid at equilibrium, which we assume via an approximation that's in the specification is the same as the concentration of the weak acid undissociated. And I'm going to demonstrate how I've got to this value on the denominator by using the information in the question. So, I've got the molar mass of the chloroxylenol just here, and I've been told by the question that for every 100 centimeter cubed of the Dettol, I have 4.8 grams of the chloroxylenol. No problem. I can then figure out how many moles that represents. So every 100 centimeter cubed of Dettol therefore contains 0.03067 mole of the chloroxylenol. Now, think carefully. If I knew how many moles were in 1 decimeter cubed, I have the moles at the moment in 100 centimeters cubed, but if I had the number of moles in a decimeter cubed, then that would mean I know the concentration. because concentration is moles per decimeter cubed. So if I know the number of moles in 100 centimeters cubed, I multiply that value by 10, and I have now the concentration of the chloroxylenol in the Dettol, which is exactly what I need. I'm also just here reinforcing that idea, because even if I was to take that mole value and divide it by the volume, which is 1 decimeter cubed, I get the same number. So I've now got the concentration of the chloroxylenol in the Dettol. Then what I need, since I've just achieved my denominator, is the numerator just here, which is the H plus ion concentration squared. I find the H plus ion concentration by doing 10 to the power of the negative pH, which was provided by the question. This quantity then gets squared, and it forms my numerator, giving me an answer for the Ka value as 1.71 times 10 to the power of negative 10 moles per decimeter cubed. Moving on to this part of the question, and we're effectively just being asked here to show with an asterisk where the chiral centre is on this other chemical compound which is found inside a bottle of Dettol, this alpha terpineol just here. So my chiral centre is here in the middle of the structure, and as you can see with my diagram on the left-hand side over here, that's because that carbon is bonded to 4 different atoms or groups. I'm counting the ring as 2 different atoms or groups because it is unsymmetrical. Moving down here, alpha terpineol meets the requirement for EZ isomerism. However, only one EZ isomer of alpha terpineol exists. Explain. We've got a series of bullet points here. Why alpha terpineol meets the requirements of EZ isomerism, whether alpha terpineol is an E or a Z isomer, and explain why only one EZ isomer of alpha terpineol exists. Right then. First off, how does it meet the requirements? It's got a carbon-carbon double bond. Each carbon in the carbon-carbon double bond is bonded to 2 different atoms or groups. That's the other criteria. It's a Z isomer. Now, have a look at the diagram just down here for why. It's a Z isomer because the 2 high-priority groups, that would be these carbon-containing sections here, are on the same side. So on my left-hand carbon, my higher priority group out of these 2 was this one at the bottom. And then out of the right-hand carbon in the double bond, out of these 2 groups, the high priority was this one at the bottom. And it's all, remember, to do with the Carn-Ingold Prelog rules that assign priority using atomic numbers. For the E isomer to exist, what we'd need to do is, instead of having this shape just here, so instead of having that kind of a shape, you would actually need to have that kind of a shape, and that would require breaking the ring in order to achieve that. Next up, alpha terpineol contains 2 functional groups. For each functional group, choose a reagent that reacts with that group only, and that's out of the other groups on the structure. Doesn't mean only ever in all of chemistry. It's saying it would only react with that part of the molecule. Draw the structures of the organic products of the reactions. Show structures for organic compounds throughout here. Clear instruction. I actually think you get more instruction on the unified chemistry exam than you think. It's just the questions can be quite intimidating. So here, the first group, if we have a look at our before just here, it's got a double bond. That means I'm going to suggest bromine. The functional group that reacts is called an alkene, and here's the product, and I've highlighted up what's changed. Next up, I've got a tertiary alcohol group. It's down here at the bottom, just there. And so I'm going to suggest for module 4 that we react this with H2SO4 and NABr. And that gives my bromine product just here at the end. So this tertiary alcohol becomes this structure just here. You didn't need to mention tertiary, but you did need to mention alcohol. I wouldn't run the risk of not mentioning tertiary here. You can't suggest things like acidified potassium dichromate to oxidize it, because that doesn't happen for tertiary alcohols, but it is worth noting that there were lots of alternatives to the answers that I've given here. Check the mark scheme for anything else, but I think these, to be honest, are the most straightforward, and I quite like that they both give bromine-containing products. This question is about copper-2 sulfate and sodium thiosulfate. The enthalpy change of reaction for converting anhydrous copper-2 sulfate to hydrated copper-2 sulfate is difficult to measure directly by experiment. Now, as you can see, as I've labelled up here, this reaction cannot be measured easily via experiment. We've got copper 2 sulfate, 5 moles of water, and then we've got the hydrated solid just here. Keep an eye on all of this. That's equation 5.1. The enthalpy change of solution of anhydrous and hydrated copper 2 sulfate can be measured by experiment. The reactions are shown below. In the equations, AQ represents an excess of water. So let's have a look here. So in these equations, I've got the copper sulfate, which is shown up there, and I've got the hydrated copper sulfate, which is shown up here. So we've already got some similarities here with the copper sulfate and with the hydrated one. Then the products here are the same from one equation to the next, and that isn't accidental. These are equations 5.2 and 5.3 respectively. Experiment 1. A student carries out an experiment to find the enthalpy of solution for reaction 5.2. So not 5.1, 5.2. Here's the student's method. They weigh a bottle containing CuSO4 and weigh a polystyrene cup. They add about 50 centimeters cubed of water to the polystyrene cup and measure its temperature. They then add the copper sulfate, stir the mixture and measure the final temperature. And then they weigh an empty bottle and weigh the polystyrene cup with the final solution. That's quite a lot of information, but it is worth noting that's quite a nice straightforward way of describing a calorimeter, and it might be worth learning how you could adapt this phrasing to other practical scenarios. We've got some mass readings here. The most important thing that we can take away from this is I'm able to get the mass of the final solution here that is in that polystyrene cup, and that's 50.70 grams. And I can also get my delta T here as 13.5, but that's fairly obvious to have done. The student carries out a second experiment, so this is experiment 2, with CuSO4.5H2O reaction 5.3. Okay, so then they go on to examine this whole setup just here. Right, they do. And the student calculates the enthalpy of solution this time. Oh, we're just given the number. It's positive 8.43 kilojoules per mole. I wonder how many people miss that. I wonder how many people miss the fact that they're just sort of telling you the enthalpy change of this equation here for 5.3. They're just casually slipping in there that the enthalpy change for that reaction is 8.43 kilojoules per mole. So what's the demand of the question? Calculate the enthalpy of solution for reaction 5.2, so that's using the student's experimental data, and determine the enthalpy change of 5.1. Ooh, that's a challenge. Assume that specific heat capacity C of the solution is the same as for water, so I don't need to think about density, thanks a lot. And show your working including an energy cycle linking the enthalpy changes. Do you know, at first glance, I bet that seems like a wow, thanks a lot, mate. That's gonna add loads of time. You can't answer this question really without that. It makes a lot of sense that they would ask for that to be included, and I'll demonstrate how you know that. First off, quick reminder, it's a level of response question. If you need some points about level of response questions and how to tackle those, I've got a separate tutorial video on my channel, which I recommend you take a look at straight after this, and I'll put the link down there in the video description. I'd also like to take this opportunity to ask you to like this video if you do use it to revise for your A-levels in chemistry, and to consider subscribing my channel so that you stay updated ahead of your exams. So let's have a look further down here. We're kicking off with an analysis of the enthalpy change of reaction 5.2. And this is all using your calorimeter setup of Q equals MC delta T over 1,000 to get the measured energy change. And then we're going to convert that into an enthalpy change by doing negative Q in kilojoules divided by the number of moles. And so all the data here should be fairly self-explanatory. I'm using M here as the mass of the final solution, whereas the mass value I use here for the copper sulfate is its actual mass. Don't muddle up your masses for this. Again, if you need guidance on what numbers to use in Q equals MC delta T, just like the level of response video, I'll put the video that describes what we're doing here in the video description. Now that I've got my enthalpy change for reaction 5.2 in a clear and well-structured answer, such as befitting for a level of response question, I can turn my attention to the cycle. And I've also made a reprint here, it was given by the question, for the enthalpy change of 5.3. Now, going back to the question, obviously you've possibly already started to look at my enthalpy cycle just here, but let's just go back to the information in the question. This enthalpy change is what we're trying to find, and the whole goal of the question is to figure out what that quantity is. So what is the enthalpy change for this reaction just here? That's the big goal. And I've got these two equations here, which have got a common feature to them in that they've got the products here are identical, and we've got this just here and that just there. So what are we going to be doing? We're going to be drawing a Hess cycle effectively, and here it is. So this is equation 5.1 shown across the top, and at the bottom here what I've got are the products here from these other reaction equations. Then what I've got is going down here on the left to create these ions, I've got reaction 5.2. Then flipping around the equation a little bit to make this CuSO4.5H2O at the top, I'm going from the ions, which is the reverse of 5.3. So 5.3 goes from the CuSO4.5H2O to the ions. Well, I'm going to flip that on its head, and in doing so, I'm going to flip the sign, indicated by a little negative here already, for 5.3. So this 8.53 is going to be changing up in just a little minute. Now, Hess states that the enthalpy change for a reaction is the same whichever route is taken from reactants to products. And what we want to do is add up this alternative route, and it will give us the one we can't find by experiment. So the calculation is quite simply just shown here. There it is. I'll just hold on the page there for a moment. But we've got 5.1 equals 5.2 and 5.3 added together. Just be careful here with that sign on the 5.3. So I've got my numbers here that I'm going to use for that. And I've got therefore my enthalpy change of negative 65.65 kilojoules per mole. I think this final stage here is really tricky. But the way I got to it was, think about your overall equation that you're trying to find the enthalpy change for as your top section that you don't have. Think about what's going to go at the bottom. Normally it's going to be things like elements or combustion products, because for a normal Hess cycle we get either enthalpy of formation or combustion data. In this scenario, since we didn't have that, we want to think, what could we put at the bottom that's common to these alternative equations I have here that are associated to this top one? Well, it's going to be the products just there. So we want to look for that common feature and use that to our advantage. Really tricky question. It was level of response. Have a good read through the mark scheme for how they allocated it. You could actually manage to get 4 or 5 marks here. Not too bad at all. But it's that accessibility of this Hess diagram that I think people would stall on. Moving on to the next part, the thermometer had an uncertainty in each temperature reading of positive negative 0.1 degrees C. A student calculates a 20% uncertainty in the temperature change in experiment 2. Calculate the temperature change in experiment 2. I have never, or at least I can't remember, seen a rearrangement of the percentage uncertainty calculation. I've never seen it. Here, what we've got is percentage uncertainty equals the plus minus value over the reading times 100, and it's the reading, the delta T, that we need. This one's quite sneaky because the numerator, since it's a temperature change, needs to have that plus minus figure from up here doubled. You would do that for a burette, for example, in a titration, because it's initial reading and final reading. It's a difference. We do it here for a delta T. You would do it in heating to constant mass for a before and after mass value. So just watch out for that numerator doubling. We rearrange to get X, and X is our temperature change. It's 1 degree C. Next up for part B, let's have a look at how many times they reference the word standard in this question, shall we? The standard enthalpy change of reaction and the standard free energy change for converting anhydrous sodium thiosulfate to hydrated sodium thiosulfate are shown below. Standard entropies are given in the table. Determine the standard entropy for anhydrous sodium thiosulfate. Give your answer to 3 sig fig. And if we didn't think they said standard enough, check out the thetas all the way through here. This is standard condition indication. So it's standard, 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 standard. And the reason they're saying it all the way through like this is because they didn't want to tell you the temperature. And by saying standard all the way through, you're meant to interpret that it's 298 Kelvin. So for part 1 here, what we need to do is delta G equals delta H minus T delta S. All the values going in here, what we're going to use this for is to rearrange and get the value of the delta S, so to get the value of the entropy change, since what we need is actually one of the values that would be used to regularly get the entropy change using products minus reactants. So I'm going to rearrange here to make delta S the subject. There's my rearrangement if you want to check that out, because I'm not sure it's included in the mark scheme. And we can see here that the value for the entropy change is negative 0.133. Now you might freak out at that, thinking that is a very low value, is that right? It absolutely is, because remember that delta S in the delta G expression is actually in kilojoules per Kelvin per mole. And if we look at the data table, which is for the entropy values for these structures over here, they're actually in joules per Kelvin per mole. So we should expect that difference, and we can adjust the figure accordingly. Then delta S, remember that delta S is super. It's products minus reactants, and the value we want is on the reactant side. So I've got my products, I've got some of my reactants, and then my missing reactant just here in terms of its entropy. A bit of rearrangement, once again, here you go, spoiling you with my rearrangement there, so you can see exactly what I've done, and it gives me a value for that missing value for entropy, which is of the anhydrous sodium thiosulfate, equal to 156. Answer needed to be given to 3 significant figures, just to make a point of why I've rounded that up at the very end. Moving on to part C. Bit of a weird one here. It goes back to bonding and then to a weird dime a bit. Sodium thiosulfate contains the thiosulfate ion S2032-. The displayed formula of S2032- can be shown below. Bit weird. Predict the bond angle. Right, you might look at this and think, well, we've never done that before. Take it back a little bit, look at the central atom. As you can see by my annotation, the central sulfur atom here is surrounded by 4 electron regions. Don't overthink it, there's no lone pairs on that sulfur in the middle, it's going to be tetrahedral. So the shape, bond angle is 109.5 degrees, and that is tetrahedral. In some of its reactions, the thiosulfate ion forms the tetrathionate ion. The S2062- ion is a dimer, which just means those two bonded together to make one molecule. Draw the displayed formula of S2062- ion. I think it's a bit of a strange question, but I think the reason they've asked it is because they want to see if you can give an answer in displayed formula, if you can interpret what a dimer is. So a dipeptide, for example, although outside of A-level chemistry, is an example of a dimer. And essentially all we're doing, the real structure for this, which was their immediate answer, although they did accept alternatives, you might want to check out the alternatives, was to just take the 2 sulfurs, so take the sulfur here, of each of them, and bond them together. So I've got 2 of this, here they are bonded together, charges were completely ignored for this. It's a weird question, just make sure you definitely used displayed formula, and you showed this bond in the middle just here. Moving on here then with question 6. This one's all about ion compounds, and there's lots of focus here on qualitative analysis in your A-level, looking at the transition elements, looking at some bits from module 3. Never underestimate periodicity, qualitative analysis, and transition elements. They are a much bigger part of the papers than you think. A student carries out the reactions in the flowchart, starting with iron 2 sulfide over here. In the boxes, first off, we need to write the formulae of A and B. So A is down here, and B is over here. So first off, let's have a look at A. So we've got iron 2 sulfide, goes into solution with some acid, and we've got FeH2O6 2+, which is a green solution. Then we have some Cl2 being used, and we make an orange-brown solution. Now we should recognise that as FeH2O6 3+ aqueous. And the way we would get to that is by changing the oxidation number of the ion from 2 to 3. So going from an oxidation number of +2 to +3. That means that the Cl2 here is behaving as an oxidizing agent, but we know that that's a possibility from our work in module 3, the halogens topic. Then that orange-brown solution goes to an orange-brown precipitate using sodium hydroxide. That's all part of the Module 5 specification, that precipitation reaction, so it's not really too difficult to know here that you're meant to be using FeOH3. The only real way you could have made a mistake here, perhaps, is if you wrote FeOH2, because you hadn't clocked that an oxidation had taken place for the ion going from +2 to +3. Then we need to figure out what's going in here. Black precipitate B with a molar mass of 247.9. Well, we're told that we have H2S just here, and that silver nitrate reacts with this to make Ag2S. I think here there's a temptation for you to completely lose what's going on in the question and suggest something in here like AgCl, AgI, AgBr. Obviously that's got nothing to do with what's going on, but I think people see AgNO3 in the exam and panic and start putting down things they're familiar with. Clue here is to use the molar mass in your favour. So we've got the 247.9 grams per mole. I want you to think about all the elements you've got so far. So that's silver, nitrogen, oxygen, sulfur, and hydrogen. How are you going to get to that? And work your way to that quantity carefully, but without putting pressure on yourself to use every element. You don't have to use that. There could be more than one product, remember. The student thinks that the reaction of iron 2 sulfide with acidified H2O is a redox reaction. Is the student correct or not? No, it's not. The student is incorrect because you've got iron 2 sulfide, and then over here, because we know that water is a neutral monodentate ligand, the ion is still 2+ over here. So no oxidation, no redox has taken place. There is no change in the oxidation numbers. Next up, write the equation for the reaction of the FeH2O6 2+ with the Cl2. So here, remember what I said earlier on, this needs to be a redox reaction. So this needs to be demonstrating how the Cl2 is an oxidizing agent. So we're going to see the iron complex ion just here look like nothing has changed until you focus on the 2+ going to 3+, and that's how the Cl2 is behaving as an oxidizing agent. Any multiple of this equation is also okay, so you could have ditched the 2's and just made sure that you had a half in front of the Cl2. Next up, construct an equation for the reaction of the H2S with the acidified manganate solution. So that's acidified manganate 7. So for this, we need to figure out what our two half equations are going to be first, because this is going to be a redox reaction. And we can see that it's in acidic conditions, so I need to use my Webb method because that allows me to follow a template, getting me two well-constructed half equations that then give this lovely overall just here. Now, if you'd like to watch a video that explains what this method is in order to get these two half equations to then get to this overall, then again, I'll put a link in the video description, but there should also be a link at the top of the screen now if you want to check that towards the end of this. First off here though, I know just in terms of analysing the question that the H2S is going to be producing sulfur on the right because of that yellow solid that was mentioned earlier. And the manganate one here is going to be making the Mn2+ because of other information provided by the question. But for this Webb method that I've used here, check out the video in the video description because that's really going to make a difference to how you construct your half equations and then your overall. Moving on to the final question, and it is level of response. It's very familiar. We've got a hydrated ionic compound called compound C, and we've got its empirical formula of FeH18N3O18. We're told that a student is investigating the thermal decomposition of compound C as outlined below, and then you've got a series of stages with loads of structures therein, each allocated a letter, and the goal of the question is to determine the formulae of the lettered structures C, D, E, F, and G. You need to show all your working and equations for the reactions. We're also mindful that this is a level of response question, as we can see up here, so subheadings and a clear, logical, well-structured line of reasoning is crucial here. My recommendation is don't do subheadings of the letters, do subheadings of the stages, because that allows you to identify where the information for the letters is coming from and you're not going to miss out on any data or information. In stage 1, the student gently heats compound C, which is hydrated, to remove the water of crystallization. we're told that this collects 0.486 grams of water, it's going to be very useful in a moment, and 0.003 mole of the anhydrous compound D. I find the first stage here quite simple, to be honest, because as you can see over here, the calculation is something you'll possibly have done quite a few times before. We have two columns, one of the anhydrous ionic substance and the other column of the water, and we need to know the moles of both of them, which is actually already given to us for D, but for the H2O we need to calculate it using the maths from the question divided by 18. The ratio between the two then is 1 to 9, and you find that by dividing by the smallest number of moles, which will be the moles of D at this stage. And once you've got that 1 to 9 ratio, you just need to bear in mind that if I go right back to the start of the question, this formula we're now learning contained 9 H2Os. So if we look down at my working out down here, 9 H2Os is going to be 18 H's and 9 oxygens from that original formula. And so if I do all of that maths essentially, so I do the full formula of C minus all of these atoms that I've now found from the 9 H2Os, I get compound D's formula. So compound D is going to be FeN3O9, which is FeNO3 when we think about common ionic substances using nitrogen and oxygen. With that 1 to 3 ratio for the nitrogens and the oxygen, we should be thinking about nitrate ions. And that's, well, to be honest, that's from Module 2, because you are taught in Module 2 to look out for that nitrate ion. Compound C, therefore, is compound D, but with the waters of crystallization still shown, so I just slap on the 9H2O. Stage 2. So what happens in stage 2? The student strongly heats 0.003 mole of compound D, which decomposes. So that means it doesn't react with oxygen, it's the only reactant, to form a solid oxide E with a molar mass of 159.6. and 270 centimeters cubed of a gas mixture measured at room temperature and pressure containing gases F and G. I'm actually going to ignore F and G at this stage as much as I can because, as I can see in stage 3, F and G are going to get a lot of attention. So I'm going to learn about what F and G are further down the process. E is my focus right now. So D gets heated and we produce E, which is 159.6, F and G, which are both gases, and we'll come back to them shortly. But we're also told by the question that E is a solid oxide. That means it contains the iron and oxygen only, because there aren't going to be gases that contain iron for the formulae of F and G. So E contains iron and oxygen. To get to 159.6, looking at the decimal in particular, considering that one iron is 55.8, we're going to have 2 ions in there, and because we know it's an oxide, the rest is oxygen. So E, therefore, has the formula Fe2O3. Moving on to stage 3. So how do we use the information in the question to figure out what F and G are? Well, we're told that gas F is a compound which condenses to form 0.414 grams of a liquid, but I actually think that's not quite useful just yet. In order to learn more about F, I need to consider it as a gas still. The 270 centimeter cubed gas mixture, we're told, is 54 centimeters cubed at room temperature and pressure of gas G. So that means if I do 270 minus 54, I get the volume of gas F at room temperature and pressure. Now, if I divide that by 24,000, the molar gas volume, I find how many moles of gas F there were in that volume, which is 0.009 mole. Very interesting, because now what I can do is find the molar mass of gas F by doing mass divided by moles, since I'm told the gas condenses to form a liquid which has a mass of 0.414 grams. That gives me the molar mass of gas F equal to 46 grams per mole. Now, this is where it gets quite complicated. In stage 2, we were told that D, which we know is FeNO3 decomposed to EF and G. E contained iron and oxygen, which means F and G contained nitrogen and oxygen only. G, I'm told, relights a glowing splint. That means G is oxygen. Bear with me here, because now that means F contains nitrogen and oxygen only. And I know its molar mass is 46, so I can put together that it has the formula NO2. That is a lot to think about all at once, but it does make sense. Let me just run through it once more with you. 270 centimeters cubed is the volume of the gas mixture F and G. We're told by the question that G is 54 centimeters cubed. That means F on its own is 216 centimeters cubed. Divide that by the molar gas volume, and my number of moles of gas F is 0.009 mol. I can then turn that into a molar mass, which allows me to identify gas F by doing the mass of the liquid it forms when it condenses, 0.414 grams, divided by this number of moles to give me 46 grams per mole. Which elements am I using to figure out the formula which has a molar mass of 46 grams per mole? I refer back to stage 2. In stage 2, the iron 3 nitrate decomposed to form E, which was iron oxide, F and G, which contain nitrogen and oxygen together. G we know is oxygen because it relights a glowing splint, meaning F uses nitrogen and oxygen in its formula, and the way to get to 46 is with NO2. For the final bit here, just on the additional answer space, which was just literally over the page, I've put the two reaction equations for the processes that are described. So if we go back to the question, in stage 1 we're describing the heat into constant mass effectively, and in stage 2 we're describing the decomposition. We're not actually getting any other reactions here as it goes further down. So the question did tell us to give equations for the reactions, it's just these two here that I'm interested in. Thank you very much for watching this very long video for the Unified Chemistry paper from 2019. Are you ready for those level of response questions? Have you revised all of the spectroscopy yet? Click the links on screen now to be taken to some of my very popular videos on these topics, and don't forget to like this video before you go and subscribe to stay updated. Check the video description as well for any other information arising from future papers associated to this content. And until next time, everybody, happy revising.